Alright, to start, let's go over the challenge problem from the last video. So we have a dog that's going to walk forward at a constant speed, and we know that the slope of a position versus time graph is our velocity, or in this case we're saying our speed. So that means we need to start out with a constant slope. Then the dog suddenly sees a squirrel and rapidly speeds up. That means we have an acceleration, and that means we have to have a period of upward curvature on our position versus time graph. And then the dog eventually slows down and stops. So that means we have a period of downward curvature because the dog is going to slow down. And then because the dog stops and sits for a short while, the dog is going to have a constant position while it's sitting, so we just have a horizontal line. And then turns around and walks back to where it initially began. So if the dog was initially going in this direction, it's now going in this direction. But it walks back at a slower speed. So that means our slope has to be decreasing, but it needs to be less steep than the magnitude of the slope. So we should have something like this. So to recap, we have a constant slope, a period of upward curvature, downward curvature, horizontal line, and then a constant slope going back to the point y equals 0 because the dog returns to its initial position. Alright, in this video we are going to be deriving the kinematic equations, or in other words, the equations that involve a lot of the variables we've already learned in kinematics, such as velocity, position, acceleration, and time. Alright, the first equation I'm going to derive for you is what I believe to be the easiest one to both derive and to use in practice. So we start out with what we already know, which is that acceleration equals change in velocity over change in time, right? And we also know that this delta symbol means we take our final minus our initial, and then we also still have our change in time, which we're just going to leave like that, right? And now it's just a matter of rearranging. So what I'm going to do is multiply both sides of this equation by delta t, and that leaves us with our final velocity minus our initial velocity equals our acceleration times change in time. And then you just add the initial velocity to both sides to get our first kinematic equation, which is that final velocity equals initial velocity plus acceleration times change in time. So the second kinematic equation isn't used a lot in practice from my personal experience, and if you were to look up AP Physics 1 equation sheet, you would see that it's not on there, but it is used to derive the remaining kinematic equations. So what we're essentially going to do is take two equations that we should already know, and then we're going to combine them. So the first one is that average velocity we know can equal change in position divided by change in time, but we could also say that it's our initial velocity plus our final velocity divided by 2, right? Because when you want to take the average, you take your first number, your last number, and then you divide by 2. And we also know that the change in position equals the average velocity times the change in time. So we have average velocity here, and we're just going to plug it in right there. So we can now say that our change in position equals our initial velocity plus our final velocity divided by 2 times our change in time. Alright, so these are the two equations we've already derived, and what we're going to do for this third equation is actually combine them. And this equation equation, from my experience, is the one that I have used the most of all of them. So we're going to take this final velocity and we're going to substitute it into this final velocity. So that gives us change in position equals our initial velocity plus our initial velocity again here. So we have twice our initial velocity plus acceleration, change in time, divided by 2 times change in time again. So I'm going to rewrite this again. So we have our change in position equals, and we're going to put this together plus this part together, and we can do that because we only have one value in the denominator. Times delta t. So these change in 2's divide out, and I'm going to factor out a 1/2 out of this denominator here. And that means now we have change in position equals initial velocity plus 1/2 acceleration times change in time times change in time. So now all we have to do is distribute this change in time out here. And that gives us our third kinematic equation, saying that change in position is equal to initial velocity times change in time plus 1/2 acceleration times change in time squared. Now, you might also see it written a different way, remembering that this delta right here can mean final position minus initial position, which equals all of this. So you could also see it written as final position equals initial position plus initial velocity times t plus 1/2 at squared. Alright, so these are the two equations that we are going to need to derive the fourth and final kinematic equation. And what I'm going to do is rearrange this equation right here to solve for t. And that's going to tell us that t equals final velocity minus initial velocity divided by acceleration. And now we have a t here and a t up here in our first equation. So I'm going to combine those, and that gives us that change in position equals initial velocity plus final velocity, or you could say average velocity, times final velocity minus initial velocity divided by acceleration. So what we can do now is distribute in the numerator and multiply in the denominator, and you will get that this equals our final velocity squared minus initial velocity squared divided by 2a. So let's multiply both sides of the equation by 2a. And that will say that final velocity squared minus initial velocity squared equals 2a change in position. And now we just add the initial velocity squared to both sides to get our last kinematic equation, which says that the final velocity squared equals the initial velocity squared plus twice the acceleration times the change in position. One thing that is really important to notice is that we've used these 5 foundational variables in each of these kinematic equations, but none of these equations have all 5 variables. This top one does not have position in it. The second one has no acceleration. The third one does not have final velocity, and this last one down here does not have time. And that's critical because it means that if you have a motion problem, you just need to know 3 of these 5 variables, and under the right conditions, such as a constant acceleration, you can calculate the other 2. That's another thing, is that these equations are only valid if you have a constant acceleration. If your acceleration is changing, and a changing acceleration is called a jerk, then you can't use these equations. Anyway, I think that it's really important to understand the fundamental concepts of how we got these equations. So my challenge for you is to give it a few hours or a day or 2 and come back and see if you can derive each of these 4 equations.